Create optical lighting and illumination and laser systems with OpticStudio, the industry-leading optical design software from Zemax.
Hello everyone, my name is Thomas Aumeyr, and today I'll be talking to you about the new ZOS API and how to communicate with it via Matlab. First, I want to generally talk about how ZOS standalone applications are generated, how we get started with this by simply making a template for programming in Matlab. I quickly explain what IntelliSense is, and then I'll dive straight into examples. The first one, we create a single lens from scratch and do a quick focus. Then we take this lens and optimize it a little bit. The next example is we take an existing lens file from the samples that are provided with OpticStudio and ran a simple analysis. And finally, I'll take a non-sequential example, run a ray trace, and then display the detector with the Matlab plotting tools. I'll talk a little bit about error handling, and then at the end you'll have the opportunity to ask me any questions in a Q&A session that follows this webinar. So how do we get connected to the API? So there's two different methods to connect to the OpticStudio API. One, with you have an application, you make your own application that is standalone, and this standalone application will start OpticStudio during its execution. This way of dealing with it is available for all programming languages that are supported. So it's for C#, C++, Matlab, and Python. And then there's the inherent way of communicating with OpticStudio, but which means that OpticStudio is already running, and it will call your application inherently. So this is only available for C# and C++. The standard so-called boilerplate code that every ZOS API application needs can be generated with the templates buttons that are available in the programming tab on the ribbon bar of the OpticStudio user interface. Here you can see how you find it. So on the programming tab, you click on standalone application under the Matlab button, and this will generate all the necessary files, set the properties, and generate an initial boilerplate code, and opens the generated solution. These projects are generated in the ZOS API projects folder of your Zemax installation path. So what does the boilerplate code do? First, it initializes a connection with OpticStudio. This can be customized. That means that you either have your standard installation path, but you can also have, if you have various OpticStudio versions installed, you can customize this yourself. So it loads the right ZOS API libraries, creates a connection class, and then creates the application that launches OpticStudio. And also it checks for a valid license to see if you're allowed to run OpticStudio. If this initialization is successful, the application will be run. And this is where the custom code comes in. At the end, the connection will be cleaned up, which means it's closed, and any sort of errors will be thrown up with a message, and the message will also be logged in a sort of simple logging system. Just a few notes about the templates. The template includes a very simple error handling. We strongly advise you to add your own style of error handling, just so like the more error interaction you have, the more stable your program becomes. For example, checking each return value of any sort of a function against null before using it is very good practice. And also wrapping the code in a try catch sort of environment will help you handle unwanted or unexpected behavior. Okay, so let's dive straight in. So as I said, let's go and see what the boilerplate code looks like. Sorry. Let's go to your OpticStudio. You under programming, as I said, you've got the Matlab button. You click it, it comes up with a standalone application. You click that, and it creates a project in your project folder, and it opens Matlab as well. I had it already open, so it dives straight in. So here you see it created Matlab standalone application 14, and has all these predefined function. So as I told you, the first thing it does, it initializes the application. If the initialization was successful, it runs this function called begin application. In this begin application is where your custom code will be contained, and finally it cleans up the connection and closes the program. Here you can see what begin application contains. So far it only imports all the libraries and creates an instance of a class called system. Here's the initialization. As I said, it loads the net helper libraries, so the API libraries, and this is a hard-coded path, but you can easily change this to whatever path you have your OpticStudio installed. It will also log a message saying that where it found the OpticStudio installation after initializations, and then after this it creates a standalone connection. If this doesn't work, again an error will be displayed and also logged, and then, as I said, it will check for if a valid license is present. If not, it will throw up the error license check has failed. And then these are functions that deal with logging messages and handling errors. And then finally here you've got the function that cleans up the connection, which basically just closes the application. Okay, so this is the boilerplate code. Let's dive straight into our first example. So as I said, our first example is creating a new file and doing a simple quick focus. Let's just open this. So as I said, I've started with the boilerplate code and just filled in my own code. So I won't be going through this again because I've just talked about this. Let's go straight into the application. So what you will have to do at the beginning of every of your codes, you will have to set up the optical system. We do this with this code here, and here you set where your samples directory is. And then we open an example, we make a file pointer that is called single lens example.zmx and is located in my Zemax, OpticStudio sample folder, sequential and objectives. The file is created and then instantly saved. And then we start off as you would do with any sort of lens file when you would do it from the user interface. So this behavior basically models exactly what you would do with the interface, a user interface. So first you will set your aperture with an aperture value of with an interest pupil diameter of 40. Then I define two field points. My first field is by default always 0, 0, so I don't have to define that. Then I define a second field point that is 0, 5. the third value is a weight of 1, which would be the default weight, but you have to add it because it requires 3 input values. Then we select our wavelength, which I have here selected as being my one of our presets. This is the preset of the D line, which is 587 nanometers. And then, like you would do in a user interface, you enter your data, your lens surfaces in the lens data editor. So again, first you create an instance that talks to your lens data editor. You insert a couple of surfaces, and here you create the instance for the surface itself. So now you have got 1, 2, 3 surfaces, and simple, you basically have, for each of these instances, you have various properties and methods, and one of the properties of surface is of course thickness. So we can change the thickness to 50, we add a comment, and we add a radius, and we do this for all 3 surfaces. If, for example, you would like to see what methods and properties are available for an instance for an instance, you could you could use something that is called IntelliSense. So rather than running the program as it is, you could enter a breakpoint. So that means that the program, rather than running all the way through, it would run until here. So, and would stop at this point. So let's see, let's run it. So you can see it stopped here, and now I can see that this little line K here, and if I now enter surface and click tab, the IntelliSense will automatically complete what is available for this for these letters. So it sees we've got when I enter surface underscore, I've got 3 objects available. They're called 1, 2, and 3. So I select 2, and to see what's available for surface 2, again I press tab. And here I get a list of all the available methods and properties that are available for this object. So if I now, for example, see I want to change my conic constant, so I go just under conic, and then I can set it to, for example, -1. And this is a way you can do this with any object, and this is really helpful. So you don't have to constantly switch back to the help and see what methods and properties are available for what object. So for example, again, if I do here for my lens data editor, what is available, I guess I press tab, and again I see all these methods and properties are available for my lens data editor. So for example, I could query what the maximum column is, what the maximum row is, and so on and so forth. As you can see, this is really helpful. Okay, let's delete this and continue. Okay, so again, so after we have defined all of our surfaces, I would like to have my third surface have an F number solve of a 10, for an F number of 10. So to do this, as you would do in the user interface, I highlight surface 3 and create a solver type on the radius cell. And to do this, and create a solver type on the radius cell and select solve type F, then enter the value for this solve type, and then finally in the user interface you will click enter or press enter, and here you just assign the solver type to the radius cell. So as you see, this is exactly how it basically just models how you're able to interact with the user interface. And then finally, I I want to have a little quick focus. So again, I set up one of my tools is called quick focus. So I open this quick focus. I select my quick focus criterion to be spot size radial. Again, in the user interface, you have this tick to use the centroid. So I use this tick, and then finally I run the quick focus. And here, instead of run, I use I use run and wait for completion. You have several types of running a tool. It's run or run and wait for completion. I have another example that uses a different way of running a tool. I'll show you later. And then finally, we close our tool, save our system, and our first file is created. So let's just run this. So let's clear our breakpoint and let's run fresh. So now the breakpoint is deleted. I run from the beginning. I get no error message because my return value is an empty array. And you see I get this empty array back. So I have the whole program ran through all the way happily. So if I now go over to my OpticStudio and open, I go on, as I said, sequential, objectives, single lens example. This is exactly what I've created. I have added two surfaces, so now in total I've got four. I have for three surfaces I added comments, I added thicknesses, I added a material, and here I've got my f-solve to be an f number of 10. And finally, I did a quick focus, which always applies to the last thickness, and it worked, and I've got my image plane at 377 millimeters. When you look at the lens, this is what it looks like, and this is exactly what we expect. So our first lens was a success. I would now like to optimize this lens a little bit, and to do so, I will use a local optimization as well as a ham optimization, and I will also, of course, for optimization, I will also have to define a couple of merit functions, and to do so, I will now have to talk to the merit function editor. So let's see how this is done. Let me close these two. So again, the boilerplate framework has not been changed. The first few lines are the same. So we open the system, define where the samples directory is. We open the lens file that we just created, so a single lens example. And we also open a pointer for a new file. We call it single lens example optimized, and save it. So save the first one as the second one. We read in, because we closed the first system, we have to get instances of these surfaces that we created. We have to get them we have to establish these instances again. Now, which you would do for any optimization, again for the user interface, you make the thicknesses and so the three thicknesses and the one radius, you make it variable, which is easy. You just have the property, the method make solve variable, and then we create a few merit functions. So as you would do, you open the merit function editor. The first operand is already there, so you don't have to add it. It will already be there by default. You just change its type. So we change its type to ASTI, which stands for astigmatism, and we target the astigmatism to be 0. And because I don't know, it's just arbitrarily chosen, I want this this is very important for me, I give it a weight of 10. And then I can just simply add operands either by giving it a specific location, or so by insert new operand at line 2, or by just add operand, which means it would just add it from below. So I also insert an operand called comma. So I target my comma to be 0 and give it a weight of 1. I wouldn't have to do these two, because by default the target will be 0 and also the weight will be 1, but it's just good practice to not lose track of the values. And now, because I want my lens to look somewhat sensible, I give them limitations on how thick the air, how thick the air and glass is set to be from a minimum and maximum. So I've got my minimum air thickness on edge and center to be 0.5, and my maximum air thickness to be 1000 millimeters. For my glass, I have a minimum air thickness at edge and center of 3, and for my thickest glass I want, like my center glass thickness, I want to have a maximum of 15 millimeters. You have, because these thicknesses go for all surfaces, you have to also assign 2 extra cells. These don't have their own names like target and weight. They are just called cell 2 and cell 3, and their values are set. So this means between surface 1 and 3, your maximum center air thickness is this value, and this applies to all of my thickness operands. Okay, so in total I've got 8 operands. And finally, I run a local optimization. Again, like you would do in the user interface, I open the optimization tool, set the algorithm to be damped least squares, set the number of cycles to be automatic, the number of cores to be set to 8, and then I will run and again wait for completion, so until it's done, and finally I close this tool. Because I think I won't be happy with this result, because I think I can, like, maybe my optimization can do a little bit better, or I want to look for, you know, a more maybe I'm stuck in a local minimum, so I want to look a bit further. I'm gonna run a hammer optimization for 10 seconds. So to do this, you open the hammer optimization tool. You run, this time you don't run and wait for completion, because hammer doesn't complete by default. So you would just run for a certain amount of time, and then I pause my code for 10 seconds, cancel my hammer optimization, and finally close my optimization tool. So this construct means that I run my optimizations for 10 seconds. You can also have the tool set up so it would run until the merit function would be lower than a limit that you could set. And finally, I save my system, and yeah, and I'm done. So let's run this. Again, I get a comment because that comes from the boilerplate where my OpticStudio installation path is located. We see it takes a few seconds. This is because the hammer optimization runs for exactly 10 seconds and it's done already. So you can see it takes exactly as long as it would do with the user interface, because the communication overhead between Matlab and Zemax OpticStudio is nigh to nothing. Okay, let's go over to the OpticStudio. Let's open, no, we don't want to save this. Let's open what we've just created, single lens example optimized. And here you can see we still have our our 5 surfaces, but now you can see that we have got 4 variables. When I open my merit function editor, I've got my 8 operands. They all have a weight of 1, except the astigmatism, which is set to 10. And here are my target values. If I want to see if I reached my goals, I can just do an update for the merit function and see that I pretty much achieved all of my targets and my merit function is very low. So now looking at how my system looks, you can see that the lens changed a little bit shape, and also the location of the lens moved a little bit inwards. Okay. Right, so let's move on to our third example. You have now seen how you make a single lens and how to optimize it a little bit. So now let's see how we can analyze our setup. And we do this by, I'm going to show you this with an example called, where is it? Here. So in this example, I'm opening an existing file that's so I'm opening a file that is called cook 40-degree field, which is one of the sample files that's provided with your OpticStudio installation. Again, system is established. We open the file, and then we create the analysis. So you create the analysis simply by creating this instance of the analyses class, and then open a new window, which is an analysis window of the FFT MTF function. So I want to create an FFT MTF, and then we need to set the FFT MTF properties. Simple, you just create an instance of the settings, which is done by the get settings function. So you can see communication with the API is super easy. So you can just directly, rather than reading in a configuration file, you can just simply get an instance of the settings, and that directly communicates with your analysis. So we read in our settings, and one of our settings is called maximum frequency, and I'm going to set this to 50 hertz. Sorry, 50 cycles per millimeter. And also I want to set my sample, so my sampling, and here I set my sampling grid of my FFT MTF to 256 by 256 points. Again, if you want to see what settings are available, you would just use IntelliSense. So you can use a breakpoint here, and then use your tab key to complete and see what settings are available. Finally, like you would have done with the optimization, you apply. So rather than run and wait for completion, in this time you apply and wait for completion. And then finally, to get the results, you just create an instance of the get results function. Again, you see there's no need to save to a text file and then read the text file. You can just directly interact with the get results method or function. And then finally, just to see what we have done, we can I open a figure, read in the data from the results, so they are stored in these data series, and then for each data series, we will, in this example especially, we have got 3 field points, so we will have 3 data series. For each data series, I'll read in both data arrays, because we will have a sagittal and a tangential set of data, and then plot them. And then finally, this is just like for cosmetics, I give it a label and a legend. So again, let's see how this runs. So you see, this is exactly, again, very quick. There's instantly you have the results on your screen, and you see we have set maximum frequency of 50 cycles per millimeter. We have got 3 data series, and Yeah, you can't see this, but the sampling was 256 by 256. Okay. What also needs to be said is that if, for example, you already have an analysis window open in your file, you wouldn't you could just simply connect to it with the API. So you don't have to recalculate the entire analysis. You can just connect to it, and the data is instantly available for you to read out and to display. So again, you would save a lot of time, and again, it makes for a very, very simple interaction and a very quick interaction. Okay, I think we've arrived on my last example. So far, all I've shown you were sequential examples. So for my last example, I will show you a non-sequential file. So hang on, let me just as a let me just run this FFT MTF again. And to convince you that we get the right result, I'm just going to show you what this would look like in OpticStudio. So let's open the FFT. So this is the this is the example file. As I said, if you, for example, want to read the data from the spot diagram, you would have to make a new spot diagram and basically create this analysis. You could just simply read the data from here. Let's see how the FFT MTF looks. So let's open a new one. Like we did in the API, we changed the sampling to 256, 256, and the maximum frequency to 50. Click OK. And let's bring up my Matlab figure, and you can see this is exactly what we just created. Okay, so now let's move on to our non-sequential example. Let's close this here. So for my last example, I thought I'd show you a simple ray trace. So again, we pick an example from our provided OpticStudio examples, which is the digital projector for the fly's eye homogenizer. We again open a tool that is called NSC Ray Trace, and then we pick it in a way you would do in OpticStudio. We select how the rays are split and scattered, if we want to use polarization, if we want to ignore the errors, and then also if we want to save the rays to a ray file. Finally, we run and wait for completion and close the tool. So now, like we did with the lens data editor and the merit function editor, we open an instance of the non-sequential component editor. We need this to get the detector data. How do we do this? We create an instance of a function called getDetectorData, and we do this. So we read out the detector data from every pixel. The way it's defined in the file, we've got a detector of 100 by 100 pixels, and we go through pixel by pixel and read it out. And finally, like I did in the previous example, a little bit of cosmetic of the plot, so it just looks a bit nicer. Okay, so first I will show you what example we are talking about. So we go on the samples, non-sequential. Where do we have it? Sorry, it's non-sequential miscellaneous digital projector flies eye homogenizer. So basically what we're trying to do is recreate this detector viewer. So as I said, we've got This is detector 4. We've got 100 by 100 pixels. And so we're recreating this. As I said, we could just read out this detector straight away without running the ray trace, but I just want to show you how the ray trace works. So let me just kick this out so it's a bit bigger. Right, let's go over and let's run the analysis. The ray trace in the UI will take you a couple of seconds, and this is the time it takes you in the user interface is exactly the same amount of time it takes you here in the API. And you can see already we have the result. So as I said, the overhead to communicate with Matlab is near to nothing, so you don't lose any time between API and user interface. So now let's go over to my OpticStudio and compare with my result. This is, as you can see, we have exactly what we would get through the user interface. Okay, these were all my examples. Let's just quickly go back to my slides. I've got a few more last slides. So thank you all for attending. I hope I could convince you that the OpticStudio API is a really flexible and helpful way to basically to make anything possible for your application. The API models exactly what you would do from the user interface. It gives you direct access to analysis settings and results to any same for the tools. You can connect to already open windows, without recalculating data, and without recalculating data. And finally, the ZOS API's applications run as fast as you would do as doing it in the user interface, so you don't lose any time. If you want to have more information, you can find them in the knowledge base article, where you can see the link here. If you have any further questions, please don't hesitate to send us an email to support@zemax.com, and but I am now available for some questions. You can submit them via the text box in the GoToWebinar control panel. So again, thanks for listening, and yeah, I look forward to hearing your questions. Thank you very much.